So when I say vertical circular motion, it becomes very obvious. It is circular motion in the vertical plane, alright. So this is a pendulum of length L and it is provided with a speed root GL at its lowest point. We have to find the minimum speed at lowest point for the bob to actually complete the circle. We have a pendulum again, but this time it is a rod. Question is, a pendulum is provided with a speed root 3 GL. So as I was talking. Hello students, welcome in today's class. Today we are going to talk about a very important topic of physics, which is vertical circular motion. But before we start with this class, I would like to tell you that you can only watch this class if you know the basics of circular motion. Like what is circular motion, what do you mean by centripetal acceleration, what do you mean by tangential acceleration. So if you know all that, then you can watch this class. Alright, so I think we can start. So when I say vertical circular motion, it becomes very obvious. It is circular motion in the vertical plane, alright? Circular motion in the vertical plane. You can correlate things by looking at these examples. A giant wheel, a pendulum or a windmill can be examples of vertical circular motion. Alright, so now we'll start with the math part of it. So the first thing, I would like to take a numerical here straight away to make you understand how vertical circular motion works. Alright, so this is a pendulum of length L and it is provided with a speed root GL at its lowest point. What we have to find is the angular amplitude of the pendulum first and the acceleration at mean and extreme position. So you have this in mind. Let's say this is a pendulum, alright, and let's say it goes up to this level. So when you provide it with a speed at the lowest point, it goes up to this level, means what? When it reaches here, its speed becomes 0. So if you know the basics, this is the mean position and this is the extreme position, alright. So now let's attempt it very quickly. Let's say it goes up to an angle theta. This is what you mean by angular amplitude. This is what you mean by angular amplitude. So you draw this diagram, you write down the question, I will wait and then we will start with the solution. You can also give it a try if you know the basics of circular motion. Alright, so if you have written down the question and also attempted it, now we can start. So let's say it is a situation like this and we have to comment on the angular amplitude. So I hope you understand that it is nothing but a concept of conservation of energy that is going to do the question. So when we say that we are going to talk about pendulum and kinetic energy converting to potential energy, we would like to believe that we are ignoring air resistance. So we can straight away apply energy conservation, that is U initial plus K initial is equals to U final plus K final. Alright, so here kinetic energy converts to potential energy at the last point. So we are obviously taking this as the reference of potential energy. Alright, so now what is the initial potential energy? You would like to call it 0. What is the initial kinetic energy? Half mv square, and in place of v square I can write GL straight away. Okay, now let's say this height is h. This height is h from mean position to extreme position. So if you understand that we are applying energy conservation, then you should understand that what is the significance of height, because you need potential energy and to write potential energy you need the height. Alright, so this is L, alright, this is L. So this is going to be L cos theta. This is going to be L cos theta. So this height is going to be L minus L cos theta. This height is going to be, this total is L, alright. This is L cos theta. So this height is L minus L cos theta. So final potential energy I am going to write mgl in bracket 1 minus cos theta. Final kinetic energy is of course 0. Final kinetic energy is of course 0 because we are talking about the extreme position. So mgl cancels out. Half is equals to 1 minus cos theta, and cos theta therefore turns out to be 1 by 2, or theta turns out to be 60 degrees. So that was easy. You have talked about vertical circular motion. Of course, now do you realize this is non-uniform circular motion, because the speed is continuously decreasing. So it is non-uniform circular motion. It is not uniform circular motion. Now, the first part is done. What is the next part? Next part, we have to find the ratio of acceleration at the mean position and at the extreme position. So let's quickly draw the free body diagram. Let's do one thing. I will draw it again. Okay, so I have this diagram here again. Since we know now this angle is 60 degree, so what I am going to do is I am going to draw the free body diagram. So mg is going to act in the downward direction, all right, and the component of mg along the string is going to be mg cos 60, while this component is going to be mg sin 60, but the velocity here is 0. So you understand what is happening here. While here mg is acting downwards and tension is acting upwards, all right, tension is acting upwards, and let's say tension here is T dash. So if you understand what is vertical circular motion now, this is nothing but circular trajectory in the vertical plane. So mg also is playing an active role now, all right. So let's quickly calculate the acceleration. So at mean position, that is this position, there is only forces in the y direction. There is no force along the x direction. So there is no tangential acceleration. So tangential acceleration is 0, while the centripetal acceleration is v square by r. Centripetal acceleration is v square by r, and since v square is gl divided by l, so the centripetal acceleration is g, all right. The centripetal acceleration is g at the mean position. Also at the mean position you can calculate the tension. How? Net force towards the center. So I am again repeating, this class is only for the students who do understand that net force towards the center is mv square by r. So if we are drawing the free body diagram here, T minus mg is the net force, and net force is equals to mv square by r. So T is equals to mg plus mv square by r. So T turns out to be mg, and this term will also become mg. So the value of T is 2 mg. So I've calculated the value of T also, and I've calculated the centripetal acceleration also, but at the mean position. What about the extreme position? This angle is 60 degree. This is mg cos 60. This is T dash. Can you write one thing very quickly, that at extreme position T dash minus mg cos 60 is equals to 0. T dash minus mg cos 60 equals to 0. Why? Because here the velocity is 0. So even if you write mv square by r, the value is going to be 0 because v itself is 0. So T dash turns out to be mg by 2. That is the tension at the extreme position. So the mean position tension is 2 mg, and at the extreme position tension is mg by 2. That means the ratio of tension here and here is 4:1. So I hope you are able to understand the basics. What is happening here? We are talking about a numerical which you have done in the past to understand how vertical circular motion works. Now, what is the acceleration at this position? So acceleration is only going to be tangential, Why? Centripetal acceleration is 0 because velocity is 0. So the tangential acceleration is simply, you can calculate that by simply equating mg sin 60, that is the net tangential force, equate that to mat. So tangential acceleration turns out to be g sin 60. Tangential acceleration turns out to be g sin 60, that is g root 3 by 2. All right. So I will repeat the whole numerical again for you because probably you were not prepared for this. Maybe you were thinking that we will first learn the topic and then start doing the numericals. But today we have done a numerical first to first check our eligibility if we are able to understand vertical circular motion. Do we know the basics of tangential and centripetal acceleration? So that is how we approach this. Alright, so we can calculate the ratio of tension, that is 4:1, and we can also calculate the ratio of acceleration. And why is it a classic example? Because here the entire acceleration is centripetal, while here the entire acceleration becomes tangential. Here the entire energy is kinetic. Here that converts completely to potential. So there is a lot going on. I hope you were able to understand. You were just writing the force equation, net force equals to ma. This is a part of work energy part because you're also involving energy here. Okay, you can copy this down and I will wait and then we move forward. Alright, so I hope you've paused the video and copied it down. Then next, now we have to talk about vertical circular motion. So what do we have to do here? We have to find the minimum speed at lowest point for the bob to actually complete the circle. So as you have seen in the previous question, it wasn't able to complete the circular motion. Why so? Because the velocity was not that much. Now this is what you have to find out. How much velocity is to be given at the lowest position, let's say A, where of course mg is acting in the downward direction, T, let's say TA is acting in the upward direction. So what I'm doing is, we have to, give it an impulse, give it a momentum, give it a velocity so that it completes the circle. It completes the circle. So when you say it has to complete the circle, obviously the thing that should come to your mind is this highest point, because this highest point is the point where its velocity is going to be minimum. So now what is the problem in completing circular motion? So the answer is, the string can slack. If the velocity becomes less, then the string can slack. The tension in the string can become 0. So to ensure that it completes the circular motion, we have to ensure that it bypasses, like it goes the highest point without any problem. So can we call this point as B? Of course we can. Let's call this C because it's the center of the circular motion. Now if we draw the free body diagram here very quickly, so this is TB acting in the downward direction, mg is also acting in the downward direction. Just now we have done this. Let's do that again. At B, let's write the net force towards the center, that is TB plus mg. Net force towards the center is TB plus mg, and that should be mv square by r. That should be mv square by r, net force towards the center. So TB turns out to be mv square by r minus mg. So can you imagine that if you rotate this with very high speed, then you would be able to rotate this completely without the string slacking, and this TB should be greater than equal to 0. Why? Because we don't want the string to slack. So this gives us VB should be greater than equal to root GL. VB should be greater than equal to root GL. This is the minimum speed that we need at the highest point. Alright, so at the highest point, this is the speed we need. But where are we starting this motion? From the lowest point. So how can we relate the speed at the lowest and the highest point now? How can you do that? Of course you can do that by applying conservation of energy, just as we did in the previous numerical. UA plus KA equals to UB plus KB. Now what is UA? UA is of course 0. Why is UA 0? Because we are taking this as the reference level. We are taking this as the reference level. Alright. Now what is KA? What is KA? Half mVA square. Very easy. What is UB? What is UB? So that is the potential energy at highest point, and can we all understand that the height from this point to this point is going to be 2L, alright, plus kinetic energy half mVB square. So this gives us an equation VA square is equals to VB square plus 4GL. Alright. So this is the equation governing the speeds at A and B, relating the speeds at A and B. Alright. I hope you were able to understand. I am starting, like I am doing the equations and the basic concepts very quickly, because I do expect that you know all these things, that net force is MA and energy conservation. This is something that you know. All right. So this is VA square is equals to VB square plus 4GL. Since we have to find the minimum value of A, so we put the minimum value of B, that is GL. So the answer is going to be VA square is equals to 5GL, is equals to 5GL. So what is the velocity that you need? Answer is anything greater than root 5GL. Anything greater than root 5GL. Okay. So at the lowest point you should give it a velocity at least root 5GL or more if you want this to complete the circular motion. But you cannot give a very high speed also, because then the string can break. So then you will have to talk about the breaking strength of the string or the breaking tension of the string. But normally you assume that the string is not breaking. So you need to provide it with a velocity. How much? You keep in mind root 5GL if you want this to complete circular motion. Alright. Root 5GL at the lowest point and root GL at the highest point. Alright. Are you understanding this equation? TB is equals to mv square by L minus mg. We equated this, or we kept it greater than equal to 0, because we did not want this string to slack. So tension has to be there. So the string should not slack. Now you might just wonder, what if it's equal to 0? Even if it's equal to 0, we'll take that case, because then the bob is going to move forward and then again the speed will be there and the tension will retain back. So even if it's momentarily 0, that's perfectly all right. Okay. You can copy this down. So we've given the answer to this part. What is the speed needed at the lowest point? The answer is going to be root 5GL. All right. Now let's talk about it again, because I wish to talk about one thing here, that let's say mg and this was TA, and at the highest point this was mg and this was TB again. So just at the highest point you wrote, that is at B, you wrote TB plus mg is equals to mv square by r. So TB is equals to mv square by r minus mg. This was the tension function. Alright. Similarly, if you write at A, listen to me very carefully. If you write at A, what are you going to write? Now you're going to write TA minus mg. TA minus mg, net force towards the center. TA minus mg is equals to mv square by r one more time. But this is for B and this is for A. What am I wanting to find out? Difference in tension. Difference in, because this is also a very common question, that tension is of course more at A and it is less at B. So difference in tension at A and B. Alright. So I'm going to subtract the two equations, TA minus TB, alright, minus 2mg. Okay, let's keep this as the first equation. Let's say, let's do this, let's call this as the first equation. So this will be much easier for you. So what am I doing now? I'm subtracting equation 1 from equation 2. So what is this giving me? TA minus TB. TA minus TB is equals to, what is it? This is going to be TA minus TB minus 2mg is equal to m by L VA square minus VB square. Alright, so I call this as the first equation and let's call this as the second equation, and then I'm subtracting equation 1 from equation 2. This is giving me TA minus TB minus 2mg is equals to m by L VA square minus VB square. Shouldn't be a problem. Now if you look at the previous page, VA square is equals to VB square plus 4GL. That is VA square minus VB square is 4GL because of energy conservation. So let's put that value again. TA minus TB minus 2 mg is equals to m by L times 4GL. So what have I done here? VA square minus VB square. I have substituted that as 4GL. So this L and L term cancels out and TA minus TB turns out to be 6 mg. Turns out to be 6 mg. So keep that in mind, that of course this is the point where the tension is maximum and this is the point where the tension is minimum. The difference in the maximum and the minimum tension is equal to 6 mg, is equal to the 6 times the weight of this bob. Alright. So are you understanding vertical circular motion? I hope there should be no problem in writing the equations. Net force is equals to ma, that is net force is equals to mv square by r. Just the difference is that at lowest position TA is acting inward, mg is acting downwards. So TA minus mg is mv square by r, while at B it is TB plus mg equals to mv square by r. Alright. So I hope you are able to understand. You copy this down. Then I wish to talk about one more case. Alright. Alright. So I hope you've copied this down. So one more case I wish to talk about is what will happen, or what is the limit that we can give to this velocity so that it behaves as a pendulum. It behaves as a pendulum means it will take a U-turn from this point. It will come, let's call this point as D. So it will not go beyond D. So that we can call it as to behave as pendulum. To behave as pendulum. So you would say in this case there is a limit that it should not go beyond this point D. It should not go beyond this point D. So you will quickly write UA plus KA equals to UD plus KD, that is initial potential plus kinetic is equals to final potential plus kinetic. Now what is initial potential? Since we are taking this as the reference, 0. What is this? Half m VA square. What is this? MGL. Alright. Why? Because the height difference from here to here is L. And what is the kinetic energy at D? 0. So the value of velocity at A turns out to be root 2GL. So this is the limit. You cannot give a velocity more than root 2GL. If you do that, then it will waver from its pendulum behavior. It will not return back from here. It will not be mean and extreme like that conventionally. So to behave as pendulum, velocity at A should be greater than 0 but less than root 2GL. So I have given you both the extreme cases. If you want this to complete the circular motion, then you should give a velocity more than root 5GL. If you want this to behave as a pendulum, then the velocity at A should be less than root 2GL, as was the case in the first question where we gave it a velocity of root GL, then it turned back after 60 degree. Alright, so keep that in mind. But now you must be wondering what's going to happen if V is greater than root 2GL but less than root 5GL, right? So greater than root 2GL but less than root 5GL. So it will go beyond this pendulum behavior, but it won't be able to complete the circular motion also, and the string will slack somewhere the string will slack and it will return here following some other trajectory than the circular motion, because the string will slack. Now the string has slacked, so the pendulum would be like this. So it will be like a projectile. So it won't be able to complete the circular path, but at the same time it won't be able to behave as a pendulum. But that will happen when velocity is more than root 2GL but at the same time less than root 5GL. Keep that in mind as well. Alright, you can copy this down and then we take one more case. Alright, so very quickly let's talk about a case where we have a pendulum again, but this time it is a rod. It is a massless rod. So with the rod, the convenience is that it can never slack. it can never slack. So if you talk about highest point, this time let's say B, since it can never slack, you can also do with velocity 0, because even if it reaches here, it will complete the circle, because the string will never slack, because it's not a string, actually it's a rod, it's a massless rod. So now the condition changes. Just keep this in mind, that if it's a rod, then you do apply conservation of energy again. UA plus KA is equals to UB plus KB, and you straight away put KB as 0. So you don't want this rod to have any, or this pendulum or this bob to have any velocity at the highest point, because we are talking about the minimum velocity right now. Alright, so UA is 0. Why is UA 0? Because that is our choice of reference. What is KA? Half mVA square. Now what is UB? That is mg into 2L. So VA turns out to be under root of 4GL. So you can provide any velocity greater than equal to root 4GL if it is a rod and you want this to complete the circular motion. Any velocity greater than root 4GL can be the can do this job, while in the case of string it was root 5GL, because at the highest point you did not ensure that the velocity has to be 0, you ensured that the string does not slack, tension was 0. So here highest point velocity is 0, in that case highest point tension was 0. Alright, so you can copy this down, then we take one numerical to finish off this short and sweet class on vertical circular motion. Alright, so the question is, a pendulum is provided with a speed root 3GL. So as I was talking, what will happen if velocity is greater than root 2GL but less than root 5GL? That is the case here at its lowest point. Then find the maximum height attained by the pendulum from its initial level. Alright, maximum height attained by the pendulum from its initial level. Alright, so let's do it. So we have provided it with the velocity root 3GL, and you do understand that the string is going to slack somewhere. So first let's assume that it slacks at an angle theta, and let's draw the free body diagram very quickly. Alright, so this is going to be mg, since this is theta, so I hope you are able to resolve vectors and everything. This is going to be mg cos theta. Let's call this point as E, and this is going to be TE. Alright, let's call the velocity here as VE. So what are we talking here? So we will write at E, TE plus mg cos theta. TE plus mg cos theta is the net force towards the center, and that is going to be mv square by r. This is what we have been doing. T plus mg cos theta equals to mv square by r. So since the string is slacking at E, so TE is 0. That means VE square can be written as GL cos theta. VE square can be written as GL cos theta. Now let's apply conservation of energy. UA plus KA is equals to UE plus KE. Alright, UA plus KA is equals to UE plus KE very quickly. Okay, so this is L. Of course, this will be L cos theta. This is L, so this will be L cos theta. So the height from here to here is this time L plus L cos theta. So what is UA? 0. What is KA? Half mVA square. Alright. What is UE? So UE is mgl 1 plus cos theta. Alright. And KE is, let's say, half mVE square. So this is what I've done. I've applied the conservation of energy 0, that is the potential energy. Initially it is 0, kinetic energy is half mVA square. Final potential energy is mgl 1 plus cos theta, and final kinetic energy is half mv square. Alright, what is the value of v square? From there we can put it as gl cos theta. So now let's plug in the values. Va square is 3gl, this is mgl 1 plus cos theta, and I can put the value of VE square as GL cos theta. I'm putting the value of VE square as GL cos theta. I've just substituted the values. It's not a big deal. Now, what are we getting? So this MGL and this 3 by 2 MGL. So this will become MGL by 2. All right. And how much is this? 1 plus half. So this is 3 by 2 MGL cos theta. All right. So from here, the value of cos theta is turning out to be 1 by 3. The value of cos theta is turning out to be 1 by 3. What do we have to find? The maximum height it will gain. It's going to be like this, as we had discussed. So we are talking about the maximum height somewhere. So it is like, you know, somewhere it's going to be at its highest point of projectile as well. So this is now behaving like a projectile with the same angle theta. So if this is theta, this is also theta. You can do this much trigonometry, geometry. This is theta, then this is also theta. So we have to calculate this height from this point to this point, which is going to be L plus L cos theta plus H max of the projectile. Okay, so let's do that. It's going to be fun. So let's do this. So what is the value of cos theta? So cos theta value was 1 by 3. Cos theta value was 1 by 3. Let's quickly do one thing. If cos theta is 1 by 3, let's draw this triangle. This is 1, this is 3. Then this is going to be 2 root 2. This is going to be 2 root 2. So we can calculate the value of sin theta also using this triangle. That's going to be 2 root 2 over 3. All right. So this was here. Then it was like a projectile and it followed this path. So we have to do this L cos theta thing first, and we have to add this H max of the projectile as well somewhere here. All right. So we have to add the 3 values. All right. So what was V square? V square was GL cos theta. And since cos theta is 1 by 3, V square becomes GL by 3. V square becomes GL by 3. I think we've done enough homework. That is the velocity at point E, to be precise. All right. So let's do it now. What is going to be the total height from initial level? The answer is going to be L plus L cos theta plus V square sine square theta over 2g. That is the maximum height of a projectile. All right. So H is equals to L plus L by 3. That is of course the value of cos theta. VE square is how much? VE square is GL over 3, and sine square theta is going to be 8 by 9 over 2g. So I've done the calculation for you. Okay, so this g and g will cancel out, and this is going to be H is equals to L plus L by 3 plus this is going to be 4. So 4L by 27. So if we take the LCM, the value of H will turn out to be 27L, and this is going to be how much? So this is going to be 27 plus 9, 36, 36 plus 4, 40. All right. So this is the maximum height. So I hope you've understood the third possible case where the pendulum is like the bob is not behaving like a pendulum also, and it is unable to complete the circular motion also. So this was theta. This is also theta. So what I did was L plus L cos theta plus the maximum height of the projectile. So this was my attempt to explain and accommodate all the possible concepts of vertical circular motion. But again, you will be only able to understand this class when you know what is vertical, what is circular motion, what do you mean by tangential acceleration, what do you mean by centripetal acceleration, what do you mean by energy conservation. So if you know all that, I hope you were able to understand this. But that's all for this particular class. We will share the slides with you. You can copy the things from the slides. But that's all for this class. I hope you were able to learn with us, and happy learning. Bye bye.
If you enjoyed this video, please don't forget to like, share and subscribe to our channel.